We've talked about stating hypotheses, but we haven't talked about what to do with them yet. So what is an actual hypothesis test? Well, it's a matter of observations and expectations. What happens when you expect something, but your observations don't match your expectations? Do you change your expectations, or do you question the observations? That's actually the crux of hypothesis testing. Let's walk through a few examples. Now let's go back. Confidence intervals we talked about. If we don't know what a population proportion is, we can take a sample and get an interval estimate for it. In contrast, if we weren't sure, but we thought we knew something about it, we might come up with a hypothesis test, also called a significance test, that's used to confirm or reject a claim about the population parameter. So here's our example. A news item says that 23% of cars on the road have no insurance. An expert reads that and says, I think it's higher than that. Well, that gives him a research hypothesis. He questions the claim. He doesn't have any data yet, but he questions the claim. So his research hypothesis is that the population proportion of cars on the road that are uninsured is higher than 23%. The null hypothesis then is equal. The null hypothesis is always equal. Now to do his test, you go out and take a sample. So we'll do that. Let's suppose we take a sample and we get 126 cars and 38 of them are uninsured. Well, our sample proportion is 30.2%, 0.302. Notice that is a p-hat, and the hypotheses were about pi's, population proportions, sample proportion, population proportion. So what does that tell us if it's not a population proportion? Well, this looks a little complicated. Let's walk through it. If the null hypothesis is true, let's back up for a second. If the null hypothesis is true, the population proportion is 23%. And we took repeated samples of 126 cars, then we'd expect the p-hats to vary along this particular proportion. That's what a sampling distribution is. It doesn't mean that this value's changed at all. The population would be fixed, but the p-hats would vary. In this particular sample, we could get anything from this range. We landed here. We got 30.2%. So is that reasonable? If these are all the p-hats that could happen with these proportions and these probabilities, is this fairly unusual or kind of normal? And this is based on sampling distribution theory. So how do we decide, well, does it look like it's way out there or does it not? Well, we could go with looks, or we can actually do some calculations to say, is this particular outcome consistent with being from this population or not? We have to compute something called a probability value. It's the probability that one would get a point estimate this far away or even further from the sampling distribution when the null hypothesis is true. Let's go back in the picture, see what that means. It says if the null hypothesis is true, so this is the distribution of all the possible p-hats, the probability value is the probability of landing right here or further, but again only when this is true. So we have an observed difference between our sample p and our hypothesized pi. What's the probability we'd see something that big or bigger? So the probability the p-hat is bigger than 0.302, again when the null hypothesis is actually true. Well, the sampling distribution is a normal distribution, so we're going to find a z-score. The z-score for our value is 0.302 minus the mean of the distribution divided by the standard deviation of the distribution. We can go back real quick and look at that. So it's this value, our p-hat, subtracted from pi and divided by the standard error, or the standard deviation of this distribution. So the probability that a p-hat is bigger than 0.302 is the same that a probability of a z in a standard normal is bigger than 1.98, and that's 0.028 or 2.8%. So this z-score is just as unusual, just as far out in the standard normal as this p-hat is far out or unusual in the sampling distribution. So what do we do with that? We actually haven't really answered the question. We've got more information. Back to the original question, the researcher says, yeah, I think the population is bigger than 23%, and he gets a sample that's 30% and says, well, I'd only get a sample this big or bigger 2.8% of the time. So let's look at the process. You state your hypotheses. You select a level of significance, which we're going to talk about. Right now it's magically going to be something called 5%. It's alpha. Then you collect your sample, you check your conditions to make sure it's a random sample, you compute your sample statistics and compute your test statistic and p-value. And then you get to make a conclusion. I'm going to hold off on the conclusion. I'm going to do a few more examples. For the examples, we're going to move over to a different spreadsheet file that I've given you. It's got test templates for quite a few different kinds of statistical tests. We're going to be sticking in this world for now and eventually go on and look at that one. But you can click on there and say, here is a significance test for proportions. You'll notice the alternative hypothesis isn't actually here. So let's step through this and look at the examples and we'll see how this works. We have a population statement that 66% of consumers use discount coupons. There's your pie. A more recent survey says that 710 out of 1,000 use coupons. So you want to know, is this evidence that pi is no longer 66%? We're going to get a p-hat out of this. So let's go over and think about our hypotheses. The null hypothesis is that pi is still 0.66. Technically, we should have come up with this before we ever looked at the data, but in this case, as often happens in the real world, we have some data that says, oh, we think it might be bigger than that. So our research hypothesis is pi is bigger. So there's the hypothesis, there's the data. Let's go into here. So pi is 0.66. I said this alpha thing is just going to stay at 0.05. We're taking samples of 1,000. And our particular sample had 710 that said they use coupons. Now what's this word success? We're actually using something called a binomial distribution, partly theoretically here. And success and failure, when there's only two options in an outcome, is merely what you're looking for. It doesn't necessarily mean it's good. In this case, we're looking for people who use discount coupons. So 710 said yes, they are successes. We could have been looking for people who have some kind of injury, and if they said, yes, I have that injury, those would be successes. So it doesn't mean it's good, it just means it's what you're looking for. So here, if the population proportion is still 66%, this shows the sampling distribution for multiple samples of 1,000. We landed here. That looks pretty far out. And then it tells us the z-score for that is 3.34. If you kind of understand normal distributions, that alone would be enough for you to think, wow, that's big. And here's the p-value. And I'm looking at the one-tail p-value instead of the two-tail because I'm going to go back to my hypotheses. We were only looking for a difference in one direction. So I'm not going to do a complete conclusion, but I'm going to start with a p-value of 0.0004. It's very unlikely that we would get a p-hat of 0.71 or larger if pi was still 0.66. And that'll be a good enough conclusion for now. Let's look at the next example. We have 90% of consumers, adult consumers drink milk. A regional farming co-op wants to do a new marketing campaign and found that 657 out of 750 adults were drinking milk. And do these provide evidence that that 90% figure is not accurate? Now I want to look at the wording here. The question here was, is the population greater than 60? Here it just says, is 90% not accurate? That's going to change how we write our hypotheses. So let's go back and set this up for the next one. Null hypothesis, 90%. The alternative hypothesis, 90%. But this is no longer a greater than. It's simply not equal. So the null hypothesis says population is 90%. The research hypothesis says it's not 90%. Back here. So 90%. Our samples were, I believe, 750. And it said 657 said they drink milk. Those are successes for this. That's what we're looking for in the yes/no question. Those that say yes, they drink milk. So it lands here. If it's still 90% out of all of our samples of 750, and the null hypothesis were true, we would expect this range of possible p-hats. We got this particular p-hat. Well, what's the probability of getting that p-hat or further away? Now in this case, our alternative hypothesis just said not equal. So further either way actually lays into the problem. So we look at the two-tailed p-value, and it says that it's 2.85%. So we're not going to, again, completely state a conclusion, but I'll start a conclusion. With a p-value of 2.85%, it's unlikely that we would get a p-hat of, what was our p-hat again? 0.876. Or further away from 0.90 if pi was still 0.90. It's a little awkward, but we'll live with that. Last example. Nationwide, 46% of medical school applicants were accepted in the fall of 2016. Southern Kentucky University said 77 out of 180 of their students were admitted. Now, I said they were concerned, so I haven't done the math on it, but it sounds like that might be lower than 46%. And the president says this is just reasonable year-to-year fluctuation. Is he right? Let's write hypotheses. Since the population is 46%, since they're concerned that their group has less than 46%. I can put 0.46 in there. Our sample size and our successes, we have to go back and look. 180 was the sample size. 77 were the yes, were accepted, so those are successes. Sample size 180, 77. So 42.8% of their students were accepted in medical school who applied. So back to the same thing. This is the sampling distribution if the null hypothesis is true. which means Southern Kentucky University's overall success rate matches the national. Theirs is here. So the p-value is going to be what's the probability of getting this much success or less in a given year if overall they match the national. Since it was looking one way, it's a 0.1922 p-value. With a p-value of 0.1982, I believe is what it was. Let's go back and look again. 1922. Hat was 0.428. I'm saying that's not that unlikely. It's almost 1 out of 5 chance. So remember, the p-value is the probability of getting a p-hat this far or further from this value. And they're telling us in the template it's almost a 20% chance that if the population was 46%, if the null hypothesis were true, that I'd get a sample of 180 students that only about 43% were accepted to medical school. Now, I haven't stated a formal conclusion yet for any of these, but I wanted you to walk through that process and see how this works. We're going to come back in the next video and talk about where did this come from and how do I use that to go over here and finish my conclusions, and what are the risks I'm taking when I do that.